Hello. Hello. Am I audible? Hello. Hello. Am I audible? Hello. So, hello everyone. Good evening. So, this is the first live problem solving session for the course Introduction to Lasers. Uh, so here I will discuss some topics and also solve some problems in today's live session. So now, my name is Bhaskar De, and I am one of the course member who is going to take this live session weekly. So everyone can see this white screen, right?
Yes, sir.
Okay, thank you. So and one more thing, that during the class, if I got disconnected for some reason, please wait, then because in 5 minutes I will try to rejoin. So be patient and don't leave the class before 9. It's a request. Okay, so the topic I am going to discuss today is uh, decay of excited states. So in the first class, first week in the course, you have learned about the Einstein coefficient and a little bit of oh, so in the so today I'm going to discuss about the decay of excited state. So in the course you have been learned about the Einstein coefficient, spontaneous emission, a little bit of spontaneous emission and absorption and all those things. So the thing is okay. So now for excited cells, for say for some system, we can have these two levels, right? But here the thing is that in nature we don't see only two levels. There are multiple levels, like uh, this one, multiple excited levels. Okay, but the most general and most simple case, that will be this one, that is this two level system. Now if we now in this is the ground state and this is the excited state. Now if we excite this excite atoms or electrons to the excited state, then we will see the population in the first excited state, that is here. So for example, here some electrons are here. Now we are exciting with some kind of radiation, like we are hitting the sample, or we are shining laser light on the sample, or we are having some kind of thermal source to heat up the sample. There are lots of things, like some people excite the system with using a some kind of light source, not laser but some other light source. It can also be done with LED or something. Okay, so now when we excite this system, this thing go to this there, and we have population here. Okay, but when the excitation is stopped, then after certain time it starts to relax. So these electrons will come to this particular ground state. Okay, because it's like a it's in our nature that we the electrons like to stay in the lowest possible uh, energy. That's why it starts to relax down to the ground state. Okay, so now if I draw the system again in a little bit. So here we are, someone raised a hand or something. Yeah, what is your question? Hello. Okay, so if you guys have any question during the class, please just speak. Don't raise the hand or something. You can speak. I mean, unmute yourself and speak. So that will be better. Okay, so here this is a two-level system. One state is denoted by L and another is U. So U is for say upper level or something like that, or state, and L is for lower level or state. Okay, now we are saying this upper and lower, but in some case you will see that this lower level is basically the ground state. Yeah, yeah, you can speak your question. I mean, is it Hema or Gayatri? Someone raised a hand, I think. Okay, so so you can if you want to say something, you can speak. I mean, after raising hand, you should ask some question or some doubt. Am I audible, guys? Or
Yes, sir, audible.
okay, so I saw two people raised hand, but they did not speak anything. Anyway, okay, so basically now at certain point of time, we can think of the population at this lower level is NL and this one as NU. So this is the population at these two level, L and U. Okay, so by population I want to mean that there is some electron and here some electron. Okay, and when we have no excitation, I mean the excitation is stopped basically. Okay, then it is going to relax, so these things are going to come down to the lowest level. Okay, now this is the simplest case. So when this thing is going to relax, we'll see there is a decay in the population. That's why it is called as decay of excited states. So now this so here this decay generally follows this kind of differential equation: dnu dt equal to minus aul nu. Okay, so basically here dnu dt, this is uh, the decay with time. This is a constant. This is a proportional constant basically, and this is the population of the upper level. So basically this decay occurs with and the decay only depends on the population of the upper level, that is this one. So the more the population in the upper level, the decay will be faster. And here this AUL, so you can think of this as the one of the Einstein coefficient, but here okay, now who is okay. So now here the dnu dt is the decay with time at the upper level. So you can see that this is a basically change of the nu by the change of time, then it is equal to the minus aul nu. So basically the nu is decreasing, so that's why this minus sign is here. aul is the proportionality constant and nu is the population of the upper level. So it is a process that is based on the population of the upper level, or you can say it is based on the population density. So here basically the population is transferring to a local level or the lower level, or the excited state population is decaying. So in another word I can write AUL as the rate or which the population is being okay. Celsius. Yeah, so what is your question exactly? Celsius, can you unmute yourself and speak about the question? I mean, okay, so to explain the decay, we can just simply think of a group of atoms. Okay, so now in case of group of atoms at room temperature, like everything we are using, that's are made up of atom. Okay, and they are in their ground state, that's why we see these things are here. Okay, now all of now the atom has some electrons. Now these electrons, if we excite them, okay, if some kind of energy is applied to the atom, then, and that energy can be of any form, like it can be heat or it can be some kind of electromagnetic wave, it can be anything. Even some kind of friction can excite a atom. Okay, now the outer electron of those atoms will excite to the higher state. That is what I am showing here in a very very simple way, that is, this is the ground state, this is the first excited state. Okay, now after using that energy or exciting the system, we are exciting this electron to the first excited state. Now when the excitation source is no longer exist, or we have stopped that thermal sources, or we have stopped the friction, or turned off the light or something, then this excitation is stopped, so this particular thing is gone. Now what will happen, that this excited electron will try to go to a lower energy state, and that's why they will come to the lower level, that is the zero, that is the ground state. Now again I have shown the same thing here, but I have changed the name or the tag for this energy states or level. I have used L for the lower level and U for the upper level, because I am not saying that this lower level is the ground state or anything. I am not specifying anything. I am just using a very generalized and simple case for two level system, where the number of the electron density or anything, we can say that is NL at the L lower level and NU at the upper level. Okay, now that if there is no excitation, then it will start to decay, that is the dnu, and this decay process will follow this differential equation, dnu dt equal to minus aul nu. So here dnu dt is the decay with time for the population nu, then it is equal to minus aul nu. Yeah, Logesh. Logesh, can you hear me?
Sir?
Yeah.
Yes, sir.
Yes, sir. Yes. Tell your question. What happened? Hello.
Sir?
Yes, Logesh.
Yes, sir.
Yeah, you raised your hand, right? Okay, Logesh, if you don't have any question, then you can mute your mic.
No, sir.
So the now here this is the differential equation dnu dt equal to minus aul nu. Now here the proportionality constant aul is the rate at which the population is being transferred. So here the transferred means the transform from u to L. Okay, now this process is totally based on the population density of the upper level. So the more excited the system is, the decay will be faster, or the decay rate will be higher. Okay, so now here the dimension of AUL is 1 by time. So this is has a unit of inverse of time, or second inverse. So now if we solve this differential equation, we will have nu equal to n naught u e to the power minus aul t. So if we solve this differential equation, we will have nu equal to nu naught e to the power minus aul t. So this is the solution for the population density of the upper level. Now what this thing means, nu naught is the initial population density in level u. So this is the initial population at this upper level. So this equation actually shows us that there is a exponential decay. Okay, so if we plot it, then we will see nu t, here this is going like this. Okay, it will never go to 0, but it will go to 0 at infinity. That's the specialty of exponential function. So this one is the n. Okay, now here we can also write AUL in terms of tau, this t. So now this tau u is the lifetime of the of this excited state. So the by lifetime, what I want to say that, like, if I write this expression again in terms of tau, then it will be n u n naught u exponential t by tau u. Okay, now by lifetime, it is like here this tau u is the lifetime. Okay, so what does this lifetime means? The lifetime means after this tau u time, the population will be exactly 1 by e times of the initial population. So here I will put t equal to tau u. That will give us n u equal to n naught u e to the power minus tau u by tau u, that is exactly e. So after tau u time, the population is 1 by e times. Okay, so at t equal to tau u, that is the lifetime, population has decreased. Yes, Bharati. Bharati, do you have any question?
No, sir. No, sir.
Okay, so the population has decreased to 1 by e of its original value. Okay, so tau is u is the lifetime of level u. Now as I was saying that in real system there can be multiple levels like this one. Okay, there is no such thing as only 2 levels. We approximate everything to 2 levels, that's a different thing, but there can be many more levels. So for more general case, we will have dnu dt minus aul plus auj plus auk plus dot 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 nu equal to minus summation I aui nu. So here basically what we are saying that there is this u level and then there is this multiple wall level, that is one is L, J, K and so on. So from u we are having this kind of transition, and every one transition has a different lifetime or decay rate. So for this one it has AUL, sorry, not lifetime. Here I will use this AUL. So this is the proportionality constant, or this is the rate at which the population is transferring from U to L. So for this one is AUL, for this one it is AUJ, for this one it is AUK. Now this is the whole differential equation for particularly U level. Okay, so now if we solve this equation again, we'll have nu equal to nu naught exponential of summation I aui. Okay, so this is the same equation like this one, but this is for a sorry, not this one exactly, this one. So this is for a two level system u and l, but here there is a multiple levels. So for the equation that will show us the population density for u level u will be this nu equal to nu naught exponential minus summation aui. So here nu naught is the initial population density at level u. Now from this we can write down the lifetime, that will, so basically the lifetime is a property of a particular state, that is u. So it should not consider the transition separately. Okay, but here au yeah, so aui is the decay rate at which the population is being transformed from level u to I, and this is a property of a particular transition. Okay, so aui is a property of a transition, but tau, that is the lifetime, is a property of a state. So here when I am going to write tau u, it will give us this value summation I aui. So it is the inverse of the summation of the all a. Okay, so now I will solve one example. That is we have three levels basically, 2d 3 by 2, 2p 3 by 2 2p half. So these are some nomenclature for the atomic system where we use this kind of nomenclature, that if needed I will discuss later, but this is for a helium cadmium laser. Okay, so this is a energy states for the CD plus. Okay, now here this is a transition and this is another transition. So this transition I'll just rotate and write lambda equal to 353.6 nanometer, and this one has a equal to 1.6 into 10 to the power 5 per second. Okay, and this transition is lambda equal to 325 nanometer. So this one has a equal to 7.8 10 to the power 5 second. Okay, so this is a for the energy states for the helium cadmium laser, where the energy states is for the CD plus ion. So these three are the energy states, and there are two transition that is shown in the picture. One is this one and this one. So from here we can see that there are two lambda. So basically lambda is from lambda you can calculate the energy of the photon that is radiated from this transition. So the energy you can do by h c by lambda. So h is the Planck constant, c is the velocity of light in vacuum, and lambda is the wavelength. So the lower the lambda, the energy of the photon is higher. So basically E is going up, lambda is going down, and E is going down, so lambda is going up. So basically the energy difference between the states, so the energy difference between these two states is comparatively less, and this two state 2d 3 by 2 and 2p 1 by 2 will is higher. So basically the lambda will be lower for this one. As you can see, this is 325 nanometer and this is 353.6 nanometer. So higher the lambda, lower the power energy of the photon. Anyway, so the energy of the photon is not our main concern right now. Our main concern is to calculate the lifetime of this 2d 3 by 2 sets. So lifetime of 2d 3 by 2. So how we are going to calculate the lifetime? So basically the formula we have was 1 by summation a u I. So here the u is the 2d 3 by 2 and I is 2p 3 by 2 and 2p 1 by 2. So basically what we'll do, we will write 1, then 1.6 into 10 to the power 5 second inverse plus 7.8 into 10 to the minus 5 second inverse. That's it. So this will give us 1 by 9.4 into 10 to the power 5 second inverse. This will give 1.06 into 10 to the power minus 6 second. Okay, so this is the lifetime of the of this particular state 2d 3 by 2. So for cadmium ion, the decay that is after this particular time, so this is exactly 1.06 microsecond. After 1.06 microsecond, the population will be 1 by e times. That is the definition of tau. So after this time, the population will be 1 by E times. Okay, now we will go to another complicated problem that is not exactly complicated, but okay, I will just write certain okay, so this is the upper level, and then there are multiple lower level. There is okay, here we have okay, so here we have one upper level, and here we have a lots of lower level. Okay, so this is basically the diagram for one very well known laser that people use, that is helium neon laser. Okay, and this is the energy level diagram for neon. Okay, so from here, so the transition are basically 1 2. So here 10 transition are there. Now what we are going to do, so as you can see that there are all these transition, but we if you search in Google or somewhere, you will see that helium neon laser operates at 632.8 nanometer. So this one transition is the most intense or most feasible transition for out of this 10 transition. But when we calculate the decay of this upper level, we see we have to consider all this transition. Okay, now the decay rate I will write. So the decay rate are, I'll just start writing A1259 into 10 to the power 5, then A2 equal to 2.83 into 10 to the power 5, A3 equal to 2100 into 10 to the power 5, A4 equal to 2.26 into 10 to the power 5, then A5 equal to 6.09 into 10 to the power 5, A6 equal to 6.39 into 10 to the power 5, A7 equal to 33.9 into 10 to the power 5, A8 equal to 3.45 into 10 to the power 5, A9 equal to 13.9 into 10 to the power 5, A10 equal to 2.55 into 10 to the power 5. So all these are in the unit is basically second inverse. Okay, so basically what we have to do, we have to calculate the sum of a u I. So sum of a u I, if we calculate from here, we will have 332.10 to the power 5 second inverse. So when we calculate tau u, that will give us 1 by 332, oh, sorry, 32. Yes, hello. Okay, so 332 into 10 to the power 5, so this will give 3.01 into 10 to the power minus 8 second, that is going to give 30.1 nanosecond. So basically in 30.1 nanosecond the population at this upper level will be 1 by e times of its original value, so it will decay in 30.1 nanosecond. So it is going to decay in tens of nanosecond order, but here for the first case it is going to decay in microsecond order. So basically this decay is faster. Now these two are like some real example. Now I will go to again a little bit of mathematical basics of mathematics. So I have started with solving the differential equation, that is dnu dt equal to minus aul nu. Okay, now if I need to solve this dnu, we can rewrite it as like this one, aul dt. Okay, now we have to integrate on the both side. dnu, I am just writing this solution of this differential equation because some of you may confused how that exponential thing is coming. Now so this one will give you ln of nu minus aul t plus c. So this is the constant. To get this constant we will just put t equal to 0 and nu equal to nu naught. So this will give ln nu naught equal to c. Okay, so the equation becomes ln nu minus ault plus ln nu naught. So it becomes, this is a property of logarithm, nu naught minus ault. So now we will just take anti-logarithm and it will give nu naught e to the power ault. This will give nu equal to nu naught exponential of ault. So this is the solution of the differential equation we are using. So now the decay of excited states I have mentioned is basically so this decay of excited states, so the decay I have mentioned here is basically a radiative decay. So when there is a decay or there is a relaxation of the electron, we will have a radiation. So basically in this particular case you can see that we have the lambda is mentioned. So when this transition is happening, we are getting a light of lambda 353.6 nanometer. Okay, now again when this particular transition is happening, we are getting a lambda of 325 nanometer. Okay, but in some cases there is a decay that's taking place, but we will not have any kind of radiation out of the system. That also happens to decay to increase the rate of the process. Okay, so one of that kind of decay is polysonal decay. Here basically this electrons will collide with each other and relax to the lower level, but in this case there will be no radiation. This is known as non-radiative decay. Okay, so this happens in the atoms, but the difference between the previous decay and this decay is that we will not have any kind of electromagnetic wave coming out of the atom. There can be electromagnetic wave, that will be then radiative decay, but this one is non-radiative decay. So when we are calculating the lifetime of a system, we have to consider two things: one, decay rate, that is due to the radiative decay, and another is gamma equal to collisional decay. Now when there is a decay of this kind, the electromagnetic wave that is emitting from the sample can also be decreasing. So if we want to write that signal, we will write it like this: Et equal to E naught e to the power minus gamma naught by 2 e to the power minus I omega naught t and 0. So this is for t greater than 0, and this is for and t less than 0. So why this is written as e to the power minus gamma naught by 2? Because electric field, the intensity of this electric field will be E then E star, or here we can say modulus of E square. So E star means that it will be E naught e to the power minus gamma naught by 2 E I omega naught t. This is the oscillating part of electric field. As you know, the electromagnetic wave have a certain oscillation, and then this star means the complex conjugate, so that will give E naught again e to the power minus gamma naught by 2, because here there is no complex part, then this will be E I omega naught t. So this thing will cancel each other and we will have E naught square minus so there will be a T, gamma naught T. This is giving gamma naught. So the intensity is also decreasing here. So this is I have just very simply shown the decrease in the intensity, but this is actually the equation of spontaneous emission. Okay. So this comes from that the system will relax because it is the excited electron will go to a lower state naturally. There is no such thing as that the electrons will be in the upper level or a fast excited state or the higher excited state for infinity time. That is not possible. So it will eventually relax to the lower state and it will emit something, and that is known as the spontaneous emission. And also it happens for many other reasons, but this is one of the reasons. Okay, now what we are going to discuss, that is a Fourier transform. So Fourier transform is a process that will take you from the time domain t time to f or omega frequency. So basically omega, so that is done using this formula, E omega equal to 1 by root 2 pi minus infinity to plus infinity et e to the power I omega t. This is the law of Fourier transform. So now if we perform this Fourier transform for this particular electric field, we will see a very so basically, for example, if there is no decay, so the electric field will be like this, et e not I, this minus or plus, minus omega naught t. Okay, now if we perform the Fourier transform, we will have 1 by root 2 pi integral minus infinity to plus infinity e naught e minus I omega naught t I omega t dt. This will give root 2 pi I omega minus omega naught. Okay, and then here we'll have this thing I omega minus omega naught. Okay, now if we use the E t equal to E naught t minus gamma naught by 2 given I omega t, then we will have E omega minus infinity plus infinity 1 by 2 pi t given e to the power I omega t dt. This will give 1 by root 2 pi minus infinity E naught into minus gamma naught by 2 minus I omega naught t given I omega t dt. So this is going to give root 2 pi 0 to infinity e to the power I omega minus omega naught plus I gamma naught by 2 t dt. So this will give E naught by root 2 pi minus 1 by I omega minus omega naught plus I gamma naught by 2. This is the Fourier transform. So now if we take intensity of this modulus square of this electric field in frequency domain, then we will have intensity in frequency domain, so that will give I omega. So I omega is basically E naught square by 2 pi gamma naught omega minus omega naught square plus gamma naught square by 4. So this is the frequency profile of the electric field. Now if we plot this one, we will have this kind of line shape where the gamma naught is this one. Okay, this is I omega, this is omega minus omega naught. So basically this will be the 0 point. So this is known as the Lorentzian distribution. Also this is known as homogeneous broadening. So this is the intrinsic nature of any kind of transition. So any transition will give rise to a electromagnetic wave, and we will have this kind of homogeneous broadening in the wave. So this is the broadening. Now by this broadening, what we are actually meaning? So here when we say a laser, that laser should have a particular frequency. For example, we say that the laser has a in frequency or in wavelength, anything we can say, because it's like it's related. So this is the relation, nu equal to c by lambda. So c is the speed of light, lambda is wavelength, nu is frequency. Okay, so when you say laser is of certain wavelength, like for here we mentioned what it is, so helium neon laser, magenta. Okay, yeah, so all the things I am here writing will be shared through NPTEL, so don't worry about it, but you will get this like in 2 or 3 days, not today. Okay, so so here I am discussing that helium neon laser has this particular wavelength, or this is the most dominant one in the helium neon laser. So but that should not mean that the helium neon laser is emitting the light at this particular wavelength 632.8 nanometer. No, if it was emitting a light of 632.8 nanometer, then this thing should look like this one. This is I omega minus omega naught, and this should be the line set. This is this is known as Dirac delta, but in reality it is not the case. It will always look like this one, and it will have some burning. So basically, for example, you can say that if you are using a 700 nanometer laser, then it might have some 40 or 50 nanometer bandwidth. Okay, so from here, we can do a little bit of problem. For example, let's say I'll just write down the problem first. Given that a particular laser emits anyone has any question right now? If you have any doubt or any question regarding the things, then you can ask.
No, sir.
Okay, so given that a particular laser emits light of frequency 6 into 10 to the power 14 hertz with a spectral line width delta nu of 50 gigahertz. What is the line width of the laser in terms of wavelength delta lambda? So basically here the problem is saying that it has a it has a it, there is a laser that emits a light of frequency 16 to 10 to the 14 hertz. So if you want to calculate, you can calculate that, like you are given the nu, you know the value of c, 14, value of c is 10 to 10 to the power 8. So lambda is basically c by nu, 3 into 10 to the power 8 by 6 into 10 to the power 14. So basically it is 0.5 into 10 to the power minus 6. So this is basically 50 nanometer. No, sorry, 500 nanometer. So this is a basically laser of 500 nanometer. Now here the problem is asking about delta lambda. So how we are going to calculate delta lambda? We have this equation, we'll just take differential of it. So basically we'll do delta lambda equal to minus c nu square delta nu. Now from the problem you can see that we have the value of nu, we have the value of delta nu, we have to calculate delta lambda. So we'll just put all the value c. Okay, I'll just write down the equation again. So anyway here there is a minus, but when you are calculating numerical value you can just take the modulus, so it will be like 3 into 10 to the power 8 by nu square is 6 into 10 to the power 14 whole square into delta nu, that is 50 gigahertz I think, 50 gigahertz, so that will be 5 into 10 to the power 10. So this will give 0.04 into 10 to the power minus 9. So this is 0.04 nanometer. So this is the line width in terms of wavelength. So it has a line width of 0.04 nanometer. So basically this is the line shape. Here we have the 500 nanometer peak, and then this is just 0.04 nanometer. Okay, now again regarding this we can have a very another small example, not exactly regarding this, but regarding the transition or the energy level I was talking about. So I'll write the problem. The energy difference between the atomic levels in a non-degenerate two level system is 0.8 eV. Okay, so 0.8 ev means that this is a two level system and the energy gap between these two levels is 0.8 ev. Okay, now what we have to calculate, we have to calculate that this is AC by lambda equal to 0.8 ev. So AC by lambda equal to 0.8 into 1.6 into 10 to the minus 19. So ev is electron volt, so electron volt is converted to joule by multiplying the charge of electron. So this particular thing is the value of charge of electron minus. Now if you multiply this and then what we have to calculate, this is the Planck constant, this is the speed of light, so we have to calculate this one. So here if we calculate properly, if we put the value of Hc, then we will have lambda equal to 1.55 micrometer. So from this energy state, if the photon is emitted, then the wavelength of that particular emission will be of 1.55 micrometer. Okay, then another small example of spontaneous emission. The spontaneous emission lifetime of a two level system is 100 microsecond. If n0 is the number density of the atoms at t equal to 0 and in t is the number density after 1 millisecond, then what is the value of nt by n0? Okay, so basically here we are given tau equal to 100 microsecond, that is 100 into 10 to the minus 6. Okay, so nt equal to, from what is the equation, this one, we will use this particular equation, nu equal to nu naught e to the power nu equal to nu naught e to the power minus t by tau u, e to the power minus t by tau. So now what we know only tau. We'll put n naught e to the power minus t 100 into 10 to the minus 6. Now the t is given 1 millisecond, so now n naught e to the power minus 1 millisecond means 10 to the minus 3. 100 minus 6. Then nt by n naught will be e to the minus 10. So this is the ratio of nt by n naught. So this is how the small problems like calculating the ratio of nt of n naught, or calculating the wavelength of the emission, or like the line width in terms of wavelength can be calculated. And if you are given a complicated problem, then that will be like this one. What was it? To calculate the lifetime of a system, you will be provided with the decay rate, that is this a, and then you will be asked to calculate the lifetime, or you will be provided with this multiple states, and here will be provided with this decay rate, and you will have to calculate the lifetime of the upper limb. Okay, now here I have discussed about the line width from electromagnetic field, electric field. Now again we can discuss about that electric field from uncertainty field. Uncertainty principle. So uncertainty principle is basically gives us a constant or limitation of how accurately we can measure two variable. So can you take an example of spontaneous transition rate based on the graph of log n? I could not understand your question. Can you please uh, describe what do you mean by the example of spontaneous transition rate based on the graph? You can unmute yourself and tell me. Okay, I'm not sure what you are asking, but as far as I can understand, you are asking about this this thing. But, okay. Yes, someone can unmute themselves. I can hear their sound. Anyway, I mean, you have the access to unmute yourself. I know that. Okay. Can you try again to unmute yourself? Because I think you guys have to access to unmute yourself. Can anyone unmute themselves? I mean,
Sir.
yeah, yeah. So Logesh can unmute himself. So it might be a problem from your side, Anna side, sound. Okay, Logesh, you can mute yourself.
Okay, sir.
Okay, thank you. Yeah. Okay, so from the question you have mentioned in the chat box, I can understand that you are asking some graph of NT and not. So so NT, wait a second, I will discuss this later. First let's clarify this one. NT and not e to the power minus t by tau. Okay, yeah, I got your point. I am just trying to explain, as you cannot unmute yourself, so I'll just explain what I am understanding from your question in the chat box. So if this is the thing, then the graph will be this n t here, t here, and you will have a decay like this, and the starting point of this one here will be exactly n naught, because if you put t equal to 0 here, you will have nt equal to n naught. Okay, so the starting point will be n naught here in the y-axis. Okay, now you are talking about nt by n naught. Okay, so if I divided this thing like nt by n naught, so that will give exponential t by tau u. So this is not writing here, so this will again have a exponential kind of thing, but the change in this curve will be, this one will be at 1, exact 1, because if you put here t equal to 0, it will give nt by n naught equal to 1, because nt equal to n naught there. Okay, now coming to your question, that is the graph of log nt by n naught. Log nt by n naught. So now nt equal to n naught minus e t tau. So nt n naught will be t minus tau, and if we take log n naught, it will be minus t by tau. So minus t by tau means that it will, so this will be a this kind of curve in the negative. So this is t, this is the velocity. So here it will be start from 0. So this will be the form of the graph, that will be a straight line, and this curve will be in that side, not in the positive side, as here you can see, because the log will give always negative point, because t is greater than 0, tau is greater than 0, then this particular value will be always negative. So now what kind of example you are talking about, I am not sure, but this will be the nature of the curve. and maybe for example it will say that it will give some value of log nt by n naught equal to some minus 0.1 or something, and then they'll just ask you to calculate the value of t at which time, I mean for this particular value, calculate the value of t, the tau will be given. Also other kind of example for spontaneous emission can be given, like here you will maybe you will be asked to, yeah, so maybe they will ask to find the value of tau, and then you know that you have to take nt equal to n naught by e, so that will give you something known as, so from this curve you have to find the value of -1, that -1 will be somewhere here, and then at that point you have to know the value of that is crossing the x-axis, and this particular value will be your tau. This kind of problem can be given based on the curve. If you can unmute yourself, then it will be easier to answer your question, but as long as I can understand, this kind of problem can be given in the assignment. Anyway, so I will get back to the line width. So there I shown the calculation of line width from electric field, oscillating electric field, and that is a kind of classical analysis, you can say, or that is okay. So that is a problem with your Google Meet or something, because here I have given access to microphone. Yeah, you guys, all of you can turn on your microphone. I don't know, maybe you can leave the meeting and rejoin quickly, that might will help. Yeah, Anna sir has joined. So Anna sir, can you turn on your mic now? Okay, so I don't know what happened to your mic, but okay. So in the next class, if you can on next Friday, if you can join and turn on your mic, then please remind me of the problem you are talking about so that I can help you. Anyway, so here I am going to I have discussed the line width from classical. Yeah, welcome Anna sir. So here I have calculated the line width of a electromagnetic, the emitted electric field with a classical point of view, that is treating that electric field and taking the Fourier transform and all those things. But there is also a quantum description of the line width, and that comes from the uncertainty principle. So the uncertainty principle gives us a limit of measuring things with a certain value. So here the uncertainty principle states that the uncertainty in determining the energy width of an energy level that has a minimum uncertainty in its lifetime of delta t is obtained from the relationship delta E dot delta t is h by 2 pi. This is also known as h bar. Planck, sorry, this is not Planck, this is reduced Planck constant. Okay, so this is the minimum uncertainty in delta E and delta t. The multiplication is h by 2 pi. Also, if we consider this uncertainty, then here we have states like this. Now this is EU, this is EL. So delta EU can be written as h bar by tau u. So thus an energy level U will have an uncertainty in energy delta U. So the delta U is the uncertainty in this energy level, and then here also you can say that delta EL is uncertainty in the, so now if we want to relate this to our previous calculation, then we can write it as gamma U or H summation A U I. Again, this one can also be directly written as h bar summation j a l j. Okay, so now if we go from this picture to a realistic picture, then it will be like this. This is the upper level, this is the lower level. So here you can see that these are no longer levels, these are basically band, energy band, and now this has a, this is the delta EU, this is delta EL. Now this is there is a broadening in the energy levels itself due to the uncertainty principle, that is delta U delta EL. Then the total broadening will be ET delta EU plus delta EL. Now this uncertainty will go to, will propagate to H delta nu UL. As you know, H equal to H nu. So from this we will have this uncertainty. So then again this one can be written as h bar summation a ui plus summation a l j I j equal to h delta nu ul. Okay, now this delta nu ul n summation I a ui plus summation l so a l j j by 2 pi. Yeah, so here it is h, here it is h bar, so this one is actually h by 2 pi. So from this 2 pi comes here. So this is this thing is known as natural emission line width. So again so this is how the natural line width comes into the picture, and from here again if we calculate the I omega we will see a Lorentzian. So this is so this particular broadening is present everywhere. So whatever the sample, whatever the system is, we will always have this broadening, because this broadening is coming from the uncertainty principle, and the uncertainty principle states that we can never accurately measure the energy of any level. So it will have some kind of uncertainty, that is here it is the delta eu, here it is delta el. So when we have an uncertainty, but we have to remember that the transition always occur between two levels. So it might occur here, it might occur like this, might occur like this, might occur from somewhere middle to here, might occur somewhere here, it can occur anywhere. So it will give a lot of uncertainty in the transition, and that will propagate to, we will calculate delta et, that will be propagate to h delta nu ul. So basically the photon that is emitting, that will have this uncertainty in its frequency. So basically when we are talking about a 600 nanometer laser, it will not be a 600 nanometer laser perfectly, it will always have a some kind of broadening. So if we plot it here, it will give us this kind of broadening, and this particular thing will known as delta nu uln. And this is actually known as the FWHM, which is FWHM, full width half maximum. So full width half maximum means that in this kind of distribution, when we calculate the this is the maximum point, and then half maximum means somewhere here, and that is the width. This particular part is the delta n ul. Now we can calculate the full width half maximum of the Lorentzian we have shown earlier. That is I naught equal to I omega I naught gamma naught by 2 pi by omega minus omega naught whole square plus gamma square by 4. So this is the Lorentzian. Now what is the maximum of this distribution? So to get the maximum, we'll have to we'll basically make this part as small as possible. So minimum value of omega minus omega naught whole square plus gamma naught 4. So to calculate the minimum value of this particular expression, we have to check that when it is going to the minimum value. So here this is 1 square omega minus omega naught square, here gamma naught square by 4, so both of them are square, so the value of x square can only go to 0 minimum. So this one is already cannot go to 0. If it goes to 0, then gamma naught has to go to 0, and that will make the whole thing 0. That is not possible. So here it is possible only when omega equal to omega naught. So at omega equal to omega naught, this is going to be minimum. Now I omega naught equal to I naught gamma naught by 2 pi. Here this one is 0, and that is gamma naught squared by 4. So this will give 2 I naught pi by gamma naught. I naught. Okay, so this one is a mistake. This is pi. So this is the maximum value. This is I max. Now I max half equal to I naught by pi gamma naught. Now we have to find the value of omega, for which we will have this. So we will have I naught pi gamma naught at this side, and again at that side we will have I naught gamma naught by 2 pi omega minus omega naught square plus gamma naught 4. Okay, now here I naught go, pi and pi gone, so we will have omega minus omega naught whole square plus gamma naught square sorry. Now this will give omega minus omega naught square. Oh, sorry. This one makes 4, and then we'll have omega naught omega naught gamma by 2 because we are taking square root of this thing gamma, this thing, so it will can give us plus or minus gamma by 2. So this will give omega naught plus gamma by 2, so plus minus gamma by 2. So that means it is giving two value of gamma. So this is I omega, this is the Lorentzian, this is the I max, that is at omega naught, then omega naught minus gamma by 2, that will be at this side, and omega plus gamma by 2, that will be at that side. So basically we will have two values of omega. Omega lower value, it is omega naught minus gamma by 2, omega higher value, it is naught plus gamma by 2. So FW HN equal to omega H minus omega L, that is gamma. So this thing is gamma. That's how you calculate the full half maximum from a Lorentzian. It can also be calculated for other distribution, but here this is, I have shown how to calculate this for Lorentzian, because Lorentzian is the most intrinsic line set that we get from any kind of system, and it is also known as homogeneous Lorentzian. Okay, so basically you can see that this gamma was the decay rate, and this is also same as the homogeneous burning. So the decay rate is actually causing the homogeneous burning, and we have shown it here. Now there is two expression I will like to write again, that is I omega I naught, this is the exact Lorentzian for the homogeneous burning, UL T by 2 pi omega minus omega naught whole square plus omega UL T square by 4 I nu equal to, so this one is omega angular frequency and this one is normal frequency, I nu I naught gamma UL T by 4 pi square omega minus gamma naught whole square plus gamma UL T by 4, sorry, right, gamma UL T by 4 pi whole square. Now this is the most intrinsic decay or radiative decay. Now again there can be broadening, due to non-radiative decay that I mentioned at some point of in this class. Radiative decay, that is collisional. Then there is also broadening due to dephasing. So also there are amorphous crystal broadening, Doppler broadening. So all this bonding will be discussed in the later problem solving session. So the main objective of this problem solving session is to solve some problems, but here I am going to discuss some topics also, because that will be relevant in the class, because otherwise yeah. So I got disconnected for a few seconds or few minutes, I think. So anyway, so this is the homogeneous broadening, and then there are broadening due to non-radiative decay, that is collisional broadening, then dephasing collision, then amorphous crystal broadening, and then Doppler broadening. So all these broadening are there, and I will discuss this broadening in the next classes, or maybe I will just show some problems regarding this. But the main aim of this problem solving class is to solve some problems. Here today I have solved two problems, major problems, and then some minor problems, but I will discuss some topic in this class, because it is necessary to discuss some topics, because otherwise the problem I will solve, that will looks like irrelevant to the topic. So I will first discuss some topic and then I will solve some problems. So any doubt from your side, anyone? If anyone have any doubt, then you can ask, because
No doubt, sir.
okay, so you understand everything from today's class?
Yes, sir.
Okay,
Yes, sir.
okay, that's good. Okay, then in the next class I will discuss some more problems, and that those problems will be longer problems, I think. So I have one question, that what kind of problems you want to be discussed in the later class, because if you give some feedback, then that will help me to frame the problems. I mean, Anasai was talking about some problem, so if any other person can mention about some problem, or if you can point out the nature of the problem, that will be helpful for me, and also will be helpful for you guys. Any suggestion?
No suggestion, sir.
Okay. The thing is that in the assignment I saw some true false problem are there, so that kind of problem discussing here is like, I will try to have some true false problem discussion, but numericals are much more preferable, I think. Okay, so in the next class I will try to add some true false type of thing, because basically when you have a concept of these things, then you can easily solve those true false problem, because it's like you have to understand the concept that is written in the assignment, is it true or false. So if I discuss the topics, then that will be easy. Anyway, I will in the next class I will discuss some more problems. And okay, question 9 of first assignment. Have you submitted the first assignment? Yeah, so before submitting I cannot discuss, that is not permitted here. Actually we are not allowed to discuss the assignment problem, that is the problem. So I can discuss some relevant problem to the assignment but not exactly discuss the current problems. Okay, so I'm sorry for that. Yeah, I will definitely discuss problems of that type but not exactly the same problem. Yeah, I'm trying to gather as much problem relevant to the assignment and the course to discuss here, but that I will do in the next classes. So yeah, so for today this is it. So if you have no more question, you guys can leave the class and I will end the session. Thanks for joining everyone and good night.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Yeah, Kausturi Sankar and Gayatri, do you have anything to say?
No problem, sir.
Okay, okay.
Thank you, sir.
Thank you, sir.
Thank you, sir.